as I already said, those first roughly 20 minutes will be more targeted to the people with no experience and low experience and the people who has never used ORCA but another quantum chemistry program. I still hope that everyone else will stay with me and just wait until I'm done so that they can then also go and run their own ORCA calculations anyway. And maybe they can also take one or few things away from it. Okay, what do I'm going to cover in the next 20 minutes? I'm going to show you how you can run your first calculation. We will learn a little bit about input and output file structures, learn how to optimize a molecule, so how to run that type of calculation. So really, really basic. Learn how to use Avogadro as a GUI, which was already mentioned earlier as well. And then also particularly for the people who have never run a calculation at all, I will also give a high-level overview of the tools of the quantum chemists. But first of all, I want to ask another question. Why should you even use ORCA? So I'm pretty sure that all of you that are here have their specific reasons why they are here, so I can't really answer this question for you. However, I can answer that question for me, why I'm using ORCA. And this is actually also the answer that I would give if somebody would ask me what drove me out of the lab and in front of the screen, and why I prefer computational chemistry over lab chemistry. And that is that whatever I can imagine, I can also calculate. So particularly with a program like ORCA, which is really versatile, whatever thought experiment I want to do, I can put some numbers behind. For example, if we start really simple, I can imagine a water molecule and I can think about the structure and can think about that I have a degree, an angle of 104.5 degrees in this water molecule. So further, I can then think about what would happen if I remove one electron and we have a radical water ion then. And could wonder what is the structure. But as in life, it's always really important to not have the right answer, but often the right question. And I think this question is quite broad and I want to specify a little bit more. What I'm really interested in here is the angle of my water radical larger or smaller than in my neutral water molecule? So how can I find that out? I can answer that question by running some calculations, specifically one, and that is the one where I'm optimizing a water radical. So to do so, I have to draw a sketch first of a water molecule, which I can then feed to ORCA so that ORCA can optimize it for me. This sketch I can draw by using Avogadro, which is a graphical user interface and looks like that. In the handout session, if you have never used it, you will also be introduced to it. But I'm just going to show you here really quickly how you can draw a water molecule in a more advanced way and then in a really rough way, basically. So the advanced or the simple way is to really just click on the pen here to tell Avogadro that you want to draw a molecule, then choose your element that you want to draw, and then click on the oxygen, click on the GUI, and you have your water molecule. So why it's directly creating a water molecule? Because we're adjusting for hydrogens. So this is a really easy way to already get quite a good starting structure, but we want to make it more complicated here to already get a broader idea of how to use Avogadro. So I'm not adjusting for hydrogens. Instead, I'm drawing just my oxygen, choose my hydrogen, draw that one again, see that I can't really draw, so my bonds are not really nice. So I'm grabbing the hand up here, with which you then can move the bonds to create a better structure. We can also turn the molecule in space so that you already get an idea how to use Avogadro, and even go ahead and then use an extension to optimize our structure. Good. Then we have our final structure in Avogadro, but this is not what we want. We want to do a quantum chemical calculation, so we have to export the structure somehow. And to do so in Avogadro, there's a button with which you can export it. And if you click on it, you will see this pop-up window in which you can save your structure to a specific file. So the file that I'm choosing as a name is H2O XYZ. H2O, since it's water molecule, so I guess it's quite reasonable, and XYZ because we're saving it as an XYZ structure. For everyone who has never seen that format, maybe it's quite intuitive because you can see why it's named XYZ. We have 3 different coordinates which are coordinating our atoms in space, so that we are basically drawing with that in a mathematical way. Here's a unit Armstrong to where our atoms are placed in space. Okay, with that, we already generated a sketch of our molecule that is then also readable by a human. We can understand why it looks like that, but we can also tell ORCA how our water molecule looks like. And this is what we want to do now. So we are creating an ORCA input file in which we are going to tell ORCA, this is our molecule, please optimize it. So, and to start, we have to first create an ORCA input file. this you can do with any type of text editor. If you've never worked with that, your tutor in your breakout room will probably be able to recommend something to you later on. But first of all, I created it here somehow just with a simple text editor, named it H2O again, which is quite reasonable since we're working with water again. And here the ending is quite important, the INP, to indicate that we have an input file, so that ORCA also knows this is an input file. Okay, we created our document. Now we have to add our data to this document so that we can draw a picture for ORCA, so that ORCA gets an idea, first of all, how our molecule looks like, and then what it should do with that molecule. And we communicate that with ORCA by adding, first of all, the XYZ coordinates that we created with Avogadro to our input file. I know there are also other ways. This is just the one that I'm going to stick for simplicity. I know that the expert in the rooms also know probably a lot of other ways to do that, but this is just the simple way how we're going to do it for the moment. Okay, we included our XYZ coordinates, but ORCA doesn't know that those are XYZ coordinates, so we have to tell them. And the way to do so is by including this asterisk blocks around our XYZ coordinates and specify those are XYZ coordinates. And with that, we communicated, this is our sketch of our molecule. This is what ORCA then also reads. However, this is not all the information that we have about our molecule here, but also the charge and multiplicity is always really relevant, and we have to include it in the input file, particularly in a case like this, because we know that here the charge and multiplicity is really what is the dividing factor between our neutral molecule and our ionic radical, right? So since we want to calculate the second one, we're including here the charge 1 and the multiplicity 2. Good. With that, we communicated to ORCA already how our molecule looked like, but now we also have to communicate to ORCA how to describe it from a quantum chemical perspective. And this brings me to my next point here, that I want to give a really high-level overview of the quantum chemist tools. And for that, I'm already really sorry to the experts. This is really the next 2 minutes is just for the people who have no experience at all, because I'm going to talk about basis sets and DFT functionals. And I know if you never heard about it, it sounds like gibberish, but if you heard about it, that what I'm going to tell you will be, first of all, probably really redundant and way too simplified so that you probably think it's entirely off. Okay, so the XYZ coordinates only describe our nuclei in space. However, we know that the chemistry is happening mainly through the electrons. So we have to define somehow our electrons. And we know the electrons are defined by the wave function in our Schrödinger equation, which is defining our entire system in general. But we also know we can't solve the Schrödinger equation for a multi-electron system accurately. So we have to somehow approximate our wave function to describe our electrons. And we do that by basis sets. Basis sets are sets of basis function to approximate the wave function overall. And there are different types of it. So you can think about it a little bit like basis sets filling in our sketch that we have the electrons in between the nuclei that we defined. And there are different sizes of basis sets. I have here a def2 basis sets type, which is quite popular, particularly if you do DFT calculations, and 3 different sizes of basis set. And if you think about it, if you have like a really small basis set, it's like brushing in the electrons with a really, with a brush with quite rough strokes. While if you go to larger basis sets like def2 quadruposita, which is the one on the right-hand side, you're brushing in with a really small paint where you can paint in quite a lot of details. So why not always go for the details? Because with increasing basis set size, you're always increasing your calculation time by quite a lot. So always think about your intent. Here, we are not really interested in a really accurate calculation. We are interested in a calculation which will represent our system accurate enough so that we can make a call about the question if our angle is larger or smaller than the one in the neutral one. So going for a medium-sized basis set will probably be enough. But before we're going for that, just here also a quick interlude that there are different types of basis sets which can be used for different purposes. Here I just make a comparison of 2, so just that you know that def2 are not the only basis sets that exist. I'm still going for the def2, and as I already said, I'm going for a medium-sized one, and I can just include it in my input file in the way that I just included by writing it in my input file. Here it's really important that you start your line in which you're including your basis set with an exclamation point. ORCA always needs an exclamation point if you just put a simple keyword in the input file, otherwise it will not recognize it as such. So always start your line before you're including your keywords with an exclamation point in your ORCA input file. This is really important. I know there are also other ways to include keywords for the expert in the rooms, but this is just for simplicity. This is what we are sticking for this session. Okay, so we described our electrons. However, we also want to solve the entire Schrödinger equation. We want to get our energy or other properties. So we need a method to calculate our energy and properties in general. And there's also a bunch of different methods out there, which will more and more accurately describe your system, starting from semi-empirical methods, which were already mentioned in the previous session, where you get a rough idea again of your system. And the higher you get over DFT to wave function methods, you get a way more natural picture, basically, of your molecule, and way more accurate one. However, in our case, we really want to make a geometry optimization, and they're going for the highest accurate method. Doesn't make sense. So always know the tool to the questions that you want to answer. In our case, DFT, fully enough. We don't have to go to wave function at all. And if you already heard of DFT, you're also absolutely familiar with the Jacob's ladder of DFT functionals, that there are also different levels of accuracy here, going from LDA to double hybrid. We are going here for the middle ground, since, again, our calculation time will increase with accuracy. So we're going for meta GGA, particularly one that is named R2scan. So this is the one that I'm just choosing here. There are also a bunch of other ones out there. And I also included in the same way my input file by starting my line with an exclamation point followed just by the name. So this is the way to include your keyword. With that, I'm already ending my high-level overview of the tools of the quantum chemists. Sorry again to all the experts in the room, and I'm going to continue with my input file. Because there are quite other things that we have also still include to make this calculation as good as possible. So you already listened to Bernardo's talk, where he also talked about explicit solvation. So the reason behind it is because typically we don't have our system in vacuum. If we do an experiment, even a thought experiment, our molecule will probably not be in vacuum. So we need to somehow simulate the solvent around it. And the way to do so is to include the solvent molecule explicitly. However, that is not really handy, because with every molecule that you will include, your calculation time will increase. And here we are only just interested in one molecule and in the geometry of one molecule. So it makes more sense to implicitly include the solvent by including an implicit solvent, which is thus mimicking this effect of the solvent on the molecule due to its dielectric constant. And one of the models that you can use is CPCM. There are also other ones out there. We also have Miguel here, who's an expert in that, and he will have one of the breakout rooms. So if you have questions about that, maybe bother him about it a bit more. And the way to include CPCM, again, is by just saying you want to have the method CPCM followed by the solvent that you want to include. With that, we have fully described our system. We described the coordinates. We described how to describe the electrons, the method with which we want to solve our problem, and also the background, basically. But we still always have to think about the purpose of our calculation. In our case, optimization. So we also have to tell ORCA that we want to do an optimization here by including the keyword opt. Good. With that, our input file is fully filled. But something I think that is really important, and I think it's a huge advantage of ORCA, is that the ORCA syntax is quite forgiving. Because for me personally, when I'm starting with a new quantum chemistry program, one of the biggest hurdles is to know how to structure my input file. And I think this is something where ORCA is really nice to the users, particularly to the ones of the more chaotic side, that you can kind of structure your input file a little bit like you want. So the input file that I have on the right side is the same one as I have on the left-hand side, where I just write all my keywords in one line. Or I can just distribute it over 2 lines, and the order doesn't really matter. Those 3 input files do all the same. So again, an overview, what needs to be an input file? We have to have our coordinates to describe our molecule with a charge and multiplicity, then the basis set, the method, optionally implicit solvent, not necessary, and then always specify the purpose of your calculation. If you don't specify anything, it's just a single point energy calculation, which can also be the purpose of it. Good. With that, we wrote our entire input file and can now run it with ORCA. The way to do so is by locating in your here in your folder in which you saved your input file, type in ORCA, followed by the input file, and press enter, and then your calculation is running. But if you do so, then this will happen what I'm just showing here on my screen. Your output file will just be printed directly, and it will not be saved. So to have a safe way is by writing ORCA input, and then with the larger sign, also dedicate where the output file should be written. Otherwise, it's lost. So we now run our first ORCA calculation, and we want to have now a look at our ORCA output files, and we don't really want to go into detail here. This is what the breakout sessions are then for. And I just want to put your attention to two different output files here, because you can see there are quite a lot of different ones. This is the .out in which we wrote our calculation. So those is documenting all your calculation steps, your energies, all the other properties that you calculated. And then we also have now an optimized XYZ structure, which we can visualize again with Avogadro. However, here also the output file can in principle also be read by Avogadro. I just decided to take the optimized XYZ file here. So we take now Avogadro to read our output file just by opening it in Avogadro itself. And then there is a tool as well where you can measure your molecule. So in our case, I measured just the angle in which I was interested in, got my result, which is 106.7 degree. And with that, we went through all the different points and answered our question, which of the two angles is larger? So is the angle of our ionic radical water larger than for our neutral one? And yes, the angle is larger. So this is one of the questions that I could have asked, but there could have been a lot of other questions that you could also have answered with ORCA. For example, you could have wondered how radicalizing your water molecule would have had influence on the normal mode. So how would the IR spectrum change? Or how would the reactivity with a certain other molecule change, comparing the neutral water molecule with the radicalized one? So those are questions that you could have asked and also then investigated with ORCA. And this is where we are going now over to the explanation of the structure of the hands-on session. I think we are quite good in time still. So yeah, as I already said, we are quite a diverse group. You have maybe interest in, for example, spectroscopy or reactivity, or you have never run a calculation. So we want to either advance your ORCA journey from here on out, or get you started with ORCA. And we're going to do that by creating different breakout rooms. So we are going to have high and mid-level experience breakout rooms, and also no and low experience breakout rooms. You probably know best where you fit in, depending on how you felt in the questionnaire, but also now, like, based on what I just showed. So besides the no and low experience breakout rooms, we are also going to create specialized breakout rooms, which I'm also explaining in a second. However, first of all, I want to explain to you what you are going to expect in those breakout rooms. So when I'm done with my talk in like 2 or 3 minutes, you're just going to distribute yourself, depending on your interest, in the different rooms. In the room, you will then find, most importantly, one tutor. And you will also find a list of tutorials to work on. So your task then is to work on the tutorials in your own pace. We want you to get started with ORCA. We want you to do your own calculations, to work on your own pace, and also to work on your own interest. So if one of the tutorials is not of interest to you, just don't do it. Do a different one instead. That's totally fine. And then most importantly, because your tutors shouldn't get bored, ask your tutors quite a lot of questions. So always, if something is not clear, if something is not working, or if you have just a general question, ask them. They are happy to help, and they are there to help. About the tutorials that we're going to use in the breakout rooms, we're going to use the official ORCA tutorials. As I already said, there will be a list of tutorials of specific ones in the specific breakout rooms, which I'm also going to show in a second. But just a few words to those tutorials. They are free and accessible for everyone. So this is quite nice because you can still use them after this hands-on session, and you don't have to stop here. You can continue using ORCA, using those tutorials. So this is also the reason why we chose to base our hands-on session here on the tutorials, so that you already get a feeling for the documentation and all the information is not lost after the 45 minutes. So let's have a look at the tutorials in the no and low experience breakout rooms. You can see that the topics are exactly what I already presented here, but just with different examples. You're going to learn how to run ORCA, learn about input and output file structure here, emphasis again of output files, since I kind of skipped over that. Also using Avogadro and learning how to optimize a molecule. So then we have some high and mid-level experience breakout rooms dedicated to 3 different topics. The first one is reactivity, where we decided to put the emphasis of finding transition state, calculating accurate energy barriers, and ORCA's Docker, which also Bernardo presented earlier. Then we have ORCA spectroscopy rooms 4 as well, which are going through the typical spectroscopy methods, basically. So IR, UV-Vis, and an MR. I know that those are quite diverse topics, so we decided to split those in focus rooms. So you can go to a general spectroscopy room or to rooms focusing specifically of one of those spectroscopy methods. Then we have also one other important mid and high-level experience room, which is explaining to you how to use ORCA compound scripts, which is probably a method that is still unfortunately a little bit underused in ORCA, where you're going to learn how to use scripts to create your own workflows using ORCA. Then, as I said, we have also specialized breakout rooms. First of all, we have 3 technical support rooms. We know that we said in the beginning, or like Kate sent around, that you should already pre-install ORCA and Avogadro. But I already saw in the chat that for a lot of you, it didn't work to install it, and that is totally fine. You can still stay here. You can still work with us on the hands-on session. So if you have problems with installing or any other technical difficulties, go to one of those rooms. So the first one is just in general installation parallelization. The second one is dedicated to Windows problems with ORCA specifically, and then we have a general technical support room where you can go with any general technical problems regarding Avogadro or ORCA or anything. And then we have also one other specialized breakout room, which is the ORCA Q&A, because there are also some people with really high experience, or maybe also some people that are just not interested in the topics that I just presented. And you can go to that specific room. Bernardo from the talk before will be there, and you can just squeeze in about anything that you're interested in, and he will answer all of your ORCA questions there in person. Good. Here again, an overview over the different breakout rooms. And I also have here a slide which is showing now the different tutors. Special thanks also to all the tutors who volunteered to take one of the ORCA rooms. Highly appreciated. And I think with that, I can end my talk. I'm not sure, are there any questions regarding the structure of the hands-on session, or can we just start distributing?